Hi, I'm Kirk Weiler, and today we'll be looking at the derivative of a function formally in terms of its definition with a limit. For the last few lessons, hopefully you've been playing around with approximating the slope of a curve, also thought of as the slope of the tangent line, by finding smaller and smaller delta y divided by delta x as delta x goes to 0. A lot of times we can visualize this in terms of what's known as local linearity, i.e. a smooth curve always tends to look very linear if you shrink down the domain interval over which you're looking at it. Sounds pretty impressive, but hopefully you've explored that in the last few lessons. Today, though, we're going to give it a name. We're going to say that the slope of the curve, also the slope of the tangent line at a particular value of x, is known as the derivative. It's got a lot of different symbolisms over the years because of its historical development. And we want to take a look at a few of them right now. Now, never forget, of course, that where the derivative is really coming from is the change in y divided by the change in x as the change in x goes to 0. Alright, so some of the notation is very suggestive of that. Here we have what's called df dx, and equivalently dy dx. This little d is what's called a differential, and it literally means an infinitesimal change in f divided by an infinitesimal change in x. Likewise, an infinitesimal change in y divided by an infinitesimal change in x. We also have what's called prime notation, f prime of a and y prime. Students particularly like these notations because they're easy to write, they're quick to write. I particularly like the f prime of notation because it really suggests what is true. The derivative itself is a function whose input is the x-coordinate of a curve and whose output is the slope of the tangent or the slope of the curve at that point. Now what we're really going to be getting into today are the limit definitions of the derivative of a function at a given point at a set x value and the definition of the derivative as a function itself. So I've got the two definitions written there, but what I'm going to do is I'm going to actually switch over to a different document and we're going to take a look at them in a little bit more depth. First, let's take a look at the derivative of a function at a given value of x, and we're going to specify that. We're going to call it x equals a. Now here in the image, what you can see is that red tangent line at x equals a. That's the slope of the curve. That's what we want to figure out. The reason that the limit does it, and this is really kind of neat, is that what the limit does is it takes another point. We'll draw it to the right of x equals a, but it certainly doesn't have to. It takes another value of x, and it draws the secant line through these two values. Just missed it. That was terrible. And it just calculates the slope of that line, right? The y value up here is f of x. The y value here is f of a. So without the limit, all this formula is f of x minus f of a divided by x minus a is the slope of that secant line. The brilliance of the limit now is that we take that value of x and we let it approach the value of a. That graphically means this point slides down the curve here while this point remains fixed, and that secant line rotates down to become the tangent line. It's absolutely brilliant. And we'll look at an example of it in a little bit, and we'll draw the picture for that example. What's a little bit harder for many students to understand is generating the derivative as a function itself. Now this is a little bit trickier because we don't want to specify the value of x. We don't want to say it's 3 or 5. We just want to call it x. But then when we come over here, what do we call this point? We can't call it x again. That point's already taken. So what most calculus textbooks do is they just say, all right, well, I'm just going to add a delta x on. So I'll call this x plus delta x, and therefore this must have a y value of f of x plus delta x. This must have a y value of f of x. We again get that beautiful secant line. Ugh, not so great. and we get its slope, f of x plus delta x minus f of x, of course, divided by delta x, right? That's just the change in x. And again, the beauty is now we still have this second point sliding into the first, but instead of saying that this point approaches this one, we just simply reflect the fact that delta x is going to shrink down to 0. Now, very understandably, a lot of people start to get confused here. It's very symbol heavy. There's x's, there's delta x's, there's things going to 0. Many calculus textbooks avoid using delta x, even though that's exactly what they have. And they introduce some other letter, and that's completely fine to do. Most often, the letter that they introduce is h. Now, again, all h is delta x. The reason that they do h is because they don't want you to get delta x confused with x. I think a lot of students at this level can handle the difference between delta x and x, but if you struggle with it, if it's just too many x's and too many things to keep track of and you're bothered by it, feel free, replace the delta x, I would suggest with h, but you could choose any letter you want. The plain fact is, again, all you have is y2 minus y1 divided by delta x as delta x goes to 0. So let's go back to our other document and work out some example problems. In exercise number 1, it says consider the quadratic function x squared minus 4x. Let me actually show you what this particular function looks like. Just a general sketch. We don't really need to know particularly what this thing looks like. Alright, but it's a parabola that roughly looks like this. Alright, and they ask me in letter 1 to determine the derivative's value at 6. Alright, I want to know the slope of the tangent line here at 6. So what I'm going to do is I'm going to come over here to x. Alright, again, what I'm doing, let me just go back up there so that you can see it one last time, is I'm applying this particular definition to find the slope of the tangent line, because I'm trying to find it at a specific value of x. So I'm going to come down to this curve, and I'm going to figure out the y value at 6 and the y value at x, and I'm going to create a secant line. The secant line is going to look terrible because of how poorly I've drawn the parabola, so pardon me for that. Let me just really quickly figure out what f of 6 is. It's obviously 36 minus 24. That's equal to 12. So this value is 12. Now what we're going to say about this value up here is it's x squared minus 4x, right? This one right here. So the slope is x squared minus 4x, that's y2, minus y1, over x2 minus x1. That would give us the slope of that secant line. And now what we'd like to do is we would like to make that x value, that second x value, slide into 6. Now this should take you back to limit work that hopefully you've done already in the course. If we substituted the 6 in, not surprisingly, we would get 0 divided by 0. Given that we have rise divided by run as run goes to 0, I really hope that we do get 0 divided by 0. But upon factoring, we can then cancel this out. We can now substitute, and we find a value of 8. Make no doubt about it, okay? Every time you get the value of a derivative, try your best to remember what you just found. We just found that the slope of that tangent line was equal to 8. Not 8 factorial, obviously, just 8. Because you never know. Alright, let's do the more challenging part in letter B. Letter B, it says, now we want to find the derivative function. Okay, algebraically, students tend to find this one much more difficult. But let's go back to that picture of the parabola. Alright, now I don't want the slope at 6, I want the slope at any x. So again, get our parabola in there. Yeah, okay, whatever. Alright, so let's say that I want, put it right around where we had it anyway. Let's say I want my slope at x. Right, now I'm going to go over here. I can't call that x again. I just can't. So my approach, and many people's approach, is to call it x plus delta x. Bothered by that, call it x plus h. Either way is fine. That means that we've moved over a delta x, and again, pardon my poor drawing. Now what we've got is up here, we're going to have f of x plus delta x, and we're going to have f of x. Let's write down what f of x is right here, so we just have it handy. F of x in this problem is x squared minus 4x. So we want to find the slope of the secant line going through those 2 points. Well, the hardest thing about this problem is to make sure we do this right. F of x plus delta x. Right, so that's going to be x plus delta x squared minus 4 times x plus delta x. Right, that is f of x plus delta x. Minus now f of x, right? y2 minus y1. Careful here. You're subtracting a binomial. You all know what can happen when we do that. Distribution errors. And then we're going to have delta x in the denominator. And we're going to look at the limit of that as delta x goes to 0. Now, let's take a look. I'm going to assume that students at this level are pretty good at foiling things out. So I'm going to actually multiply this binomial out in my head. I'm not going to show how to do it. You should be able to, on a piece of paper, maybe to the side somewhere. I'm going to get x squared plus 2x times delta x plus delta x squared minus 4x minus 4 delta x minus x squared plus 4x. I'm probably going to have to get rid of that graph in a moment just so I have enough room. Sorry about that. Divided by delta x. In fact, let me do that. Let me just get rid of this. There's got to be a faster way of doing that. Sorry about this, folks. Give me a second. Hey, there we go. Let's go back to the algebra. Alright, let's start to clean this up a little bit. Let's see what we can cancel. Let's see, we have an x squared canceling a negative x squared, a positive 4x canceling a negative 4x. Depending on how you've been taught to simplify fractions, you're either going to distribute division by delta x, or if you'd like, you could factor delta x out. A lot of students sort of feel safer doing that, so let me do that. Right there. Factor the delta x out of the numerator. I have that delta x in the denominator. They cancel. Don't forget to let this delta x go to 0, and you now have the derivative function, 2x minus 4. I think I'll do the next one with h, just so that you see one done that way. But remember, that function now gives us the slope of the tangent line at any value of x. Let's take a look at a classic, the square root function. Let's figure out the derivative of the square root function using the limit definition. Alright, let's draw a little picture. I really think these graphs are helpful. Again, I'm going to use h instead of delta x here so that you see a different approach. Alright, I've got my square root function, right? So I want the slope of the tangent at x. So I'm going to go here, and then I'm going to go over to x plus h. That means that my separation, my delta x, is now h. Up here, this is going to be simple. This is just going to be the square root of x. And up here, this will be pretty easy. This is going to be the square root of x plus h. So the slope of the secant line that connects the two will be the square root of x plus h minus the square root of x, right? That's y2 minus y1 divided by delta x. And now I'm going to let h go to 0. Right? That's going to force this point to slide into this point. Of course, the way that we're going to do this is we're going to rationalize the numerator, right? A limit technique that we should have learned already in the course. Let's keep doing this. Remember, we really want that h to cancel in the denominator. The numerator is going to become x plus h minus x, all divided by h times the square root of x plus h plus the square root of x Be good about your parentheses use here. Watch what happens. X minus x leaves us with an h dividing an h and a 1 in the numerator. I'm going to go for the substitution right now. Let that h go to 0. We're going to have the square root of x plus the square root of x. And that's going to be 1 divided by 2 times the square root of x. That'll be one that you'll memorize eventually. Very important derivative, the square root of x. Alright, let's take a look at letter B. Letter B asks us to sketch a graph of this function and its tangent line at x equals 4. Then, using your answer from part A, to determine the equation of the tangent line to f of x at x equals 4. At this point, the definition of the derivative isn't all that important, but let's sketch the function. I already had that in the last problem. Let's throw on a tangent line at x equals 4. I like tangent lines in red. That's not too bad for freehand. Alright, I want to know what its slope is. Let's keep the slope in red. Slope is always going to be the derivative at a particular value of x. Well, we know that the derivative is 1 divided by 2 times the square root of x. This is what's called an evaluation bar. It allows me to just say, hey, I've got a formula, and now I'm going to use it at a particular value of x. So we've got that, and of course the square root of 4 is 2. So the slope of that tangent line is 1/4. Now the other thing that they ask us to do is then write the equation of the tangent line. Alright, you'll do this many, many times in this course, and almost always you will want to use the point slope form of a line, y minus y1 equals m times x minus x1. The reason that you're going to want to do that with that form is that you're always going to pretty much know the point of tangency. That's what you're going to use as your x1, y1, and your slope is right there, right? So we've got x1, it's 4. We've got m, it's 1/4. The only thing that we tend to not have at this point is y1, but y1 will always generally be found by the function at the particular x value. Of course, that's just the square root of 4, which is 2. So we're just going to have y minus 2 equals 1/4 times x minus 4. It's the equation of that tangent line. The last thing that we're going to do, and this is kind of neat, it's very early on to be doing this, is look at why we use tangent lines. Classically, one of the things that tangent lines have been useful for is approximating nonlinear functions. The square root function is an excellent example of that. You see, it used to be that, of course, finding square roots without calculators were very hard. But the idea is that you can use the tangent line. Take a look at the geometry here. You can use the tangent line to fairly accurately predict the square root of 5, right? The square root of 5 on the line would be up here. The actual square root of 5 might be just down here. So it's a very interesting thing. We could take the equation of that tangent line. Let's put the 2 on the other side. It would be now 1/4 times x minus 4 plus 2. So if we wanted the square root of 5, we could say that that was approximately equal to this function evaluated at 5. Of course, that would just be 1/4 plus 2, which would be 2.25. Again, just visually what we're doing there is we're finding this y value right here by taking the y value off of that line. What is the actual square root of 5? Well, if we took our calculator out and we plugged it in, we'd find that the square root of 5, accurate to, let's say, I don't know, 2 decimal places, so we can compare, is 2.23. So 2.23, and our approximation is 2.25. That's pretty good. We'll be doing more of that later on in the course, so if you didn't entirely follow it, that's okay. That's it for this lesson. Thank you for tuning in. Until next time, keep thinking about math and keep asking questions. Take care.